Hi everyone, welcome to the Specialist Maths 3-4 lecture for the 8 Hour Notes January lecture series. My name is Manjot Bulla and I'll be taking the lecture today. Just before we begin today's lecture, I'd just like to go through some information about 8 Hour Notes. So 8 Hour Notes is an amazing company that has provided free resources to all high school students across Australia since 2007. And this is just to make sure that everyone has the best chance and opportunity to succeed in their academic journey. And we've also offered lectures such as the one that you're watching today since 2016. We offer a bunch of amazing free resources besides this lecture, and these include study notes, lectures, online Q&A discussions, engaging online revision videos, newsletters, 8 Hour Notes, calculator, articles, and heaps more. So if you would like to check out these free resources, please head to 8hournotes.com. And if you would like more information on how to actually access and use these resources to study, please check out the resources section of this lecture page. And if you would require even more help throughout VCE, please check out 8 Hour Notes Plus. So 8 Hour Notes Plus is sort of like a Netflix subscription type of service where we have a bunch of 8 Hour Notes topic tests, complete course notes, videos, lectures, flashcards, text guides for all the English subjects. So a lot of amazing resources to help you guys out throughout VCE. We also have stuff for year 9 and year 10. A lot of practice exams come exam time that you can use. Practice sacks, a bunch of amazing resources. And that's for all the subjects. So it's just one fee for to get a bunch of resources for all subjects, so you don't have to pick and choose. But yeah, really I encourage you guys to check that out. I personally used this resource when I was in VCE, and it really just helped me out, a lot. Okay, so let's get started on today's lecture. So just a little bit about me. My name is Manjot Bulla, like I mentioned before, and I graduated from VCE in 2022 with an ATAR of 99.80, and I'm currently studying Bachelor of Biomedical Science at Monash, and I've been tutoring at TuteSmart as a maths and science tutor for more than a year now, and the subjects that I did throughout VCE were chemistry, maths methods, specialist maths, English, biology, and further maths. It's a bit strange that I did all 3 maths, but, I just really liked the maths curriculum at the VC level compared to other subjects, so I just decided to do all of them. I know a lot of people question me about that, but anyways. So just before we begin on the actual lecture content for today, I'd like to talk everyone through about the subject. I know all of you already have a lot of information and know absolutely everything about the subject and are super excited to actually start doing the subject at school. That was probably me in VC, but just a little bit of probably just tips, I would say. As we all know, specialist maths is one of the highest scaling subjects in VCE. So the question that a lot of students will probably ask is it a great investment of their time and energy? Well, what I would like to say is that although specialist maths scales really well, you do need to put in a lot of effort and time in order to even sort of get the benefits of that scaling. So what I mean by that is if you end up, let's say you're deciding between specialist maths and further maths, let's just say, it's called general maths now. So let's just say you're deciding between those 2 subjects, and let's just say in general maths you get, 35. In specialist maths, you'll probably get like 25 if you get 35 in general. I'm not saying anything, just like an example. And then specialist maths scales to like 35. So you put in all that effort into specialist maths, you maybe compromised study from other subjects, and you end up getting the same score. So all I'm sort of like trying to tell you guys is, if you're really good at maths, or you just like the fact that this is a challenging subject and you want to, really challenge yourself, I would say definitely the best subject to do in VCE. But if you think that you might be compromising other subjects by choosing, specialist maths, just due to the fact that it requires such a big time and energy investment, then probably I would rethink my choice of doing the subject. You still have time. Nothing to deter you guys. That's absolutely not my purpose. I just want everyone to do the best that they can at VCE. Because I know a lot of students just end up doing the subject because their friends are doing it, or they're just doing it to, just for the fact that they're doing specialist maths, because there's just like this whole like popularity thing surrounding the subject, or the sort of like this preconception of the subject that if you're doing it, you must be super duper smart. So if you're doing the subject, you will be a nerd basically, or something like that. The reputation that the subject has, I would just say ignore that. Really think about what's best for you, and whether you really think it will be a good investment of your time and energy in VCE, because time is of the essence in VCE. You really do not have a lot of time to mess around, practically. However, saying that, this is a subject that requires academic resilience, patience, and commitment more than your natural mathematical ability, I would say. It's different to anything you have done prior to, prior to choosing the subject. Even specialist maths 1-2, if you've done that last year, quite different to specialist maths 1-2. So you can't really say that, I'm good at maths, so I will be good at specialist maths. Yes, it does require some mathematical background, but if you if you're thinking of doing the subject, or you are doing the subject this year, I would say the best asset to have when coming into subject is academic resilience, patience, and commitment. And when you have all these three elements, you will do exceptionally well in the subject, more than just be good at maths. Another thing that I really liked about the subject was how predictable it was. And I was told about the predictability of the subject from previous students. And that's probably one of the reasons why I chose this subject, because with, subjects that are like, for example, methods. I know a lot of students here might have already finished methods 3-4 or are doing it this year. Methods is not a very predictable subject. And what we mean by that is the type of questions that you're going to get on a methods exam from year to year varies quite significantly. And not just the type of questions, but the type of content it assesses, the type of skill sets, the type of mindset that it's, assessing or examining you on. It's quite different year to year. But specialist maths, once you look at the practice exam, you'll see what I mean about it being a predictable subject. Even the SACs as well. All the questions themselves are very similar. They might be phrased in a bit of a different way. But the thing about specialist maths is actually assessing the maths, not the application of the maths, if you know what I mean. Like, for example, with methods, it's going to give you this big scenario and it's going to ask you to sort of work out what mathematical skills you'll need to use. Whereas specialist maths, you sort of know what skills you need to use for a particular question. It's about actually using those skills. That's the major thing. And that's why specialist maths is more about the maths itself as opposed to the application of the maths. And if you're thinking of doing engineering, any type of maths, Even science, I would say at uni level, this is definitely a really good subject to do because it sort of prepares you with the mindset. And if you're doing engineering or maths, you'll probably have to do a sort of like a bridging subject anyway if you haven't done specialist maths. So why not just do specialist maths at a VC level, because it's really going to help you prepare you for uni, and the level of sort of understanding and what was I going to say? Yeah, the level of understanding and resilience that a math subject requires. It's really going to prepare you good for that. Don't be intimidated about the reputation that specialist maths has. I know going into the subject, I had heard a lot of, I'm not going to say rumors, but a lot of opinions on this subject from people that probably hadn't even done the subject and just heard it from other people who hadn't even done the subject. So people have just sort of created like this reputation of the subject of being super challenging, such an impossible subject. Only a 100 IQ person can do the subject. Really not the case. It's more about the type of mindset that you have going into the subject, which is more important. Remember, high school and the way that VCE has been designed, it's not just how good you are at a particular subject, or have a higher IQ. It's about how determined you are, how resilient you are, how much time and effort you're going to put into VCE. And that's the case for any subject. Just my personal opinion, you will either absolutely hate or absolutely love this subject. Most people go into the subject already hating it. They're like, why did I even pick this subject? And then just stop trying or just stop caring about the subject. And that's only in the first term. So that's probably why a lot of students don't do as well as they hope to, because they're already going into the subject with such a negative mindset. So what I would say, the best thing to do going into the subject is have a positive mindset. So be determined, be excited, be willing to learn new things, be willing to apply your knowledge, extend your knowledge, all that sort of stuff. That's probably going to set you up the best for success. Another thing I sort of want to talk about is how you should use these holidays, because I know everyone's going to ask that. There's still probably like 15 or so, even less, days left until school starts. The best thing to be doing now is reviewing Unit 1, 2 stuff for specialist maths. That was the basics. They're not going to cover that anymore. All they're going to do is build on that knowledge. So if your Unit 1, 2 stuff was quite weak, or you felt you could do more, you could have done more in Units 1 and 2, do that. So try to go over any SACs that you did in Year 11, any exams that you did. Go over any content that you feel you have gaps in. Try to get help from your teacher if you can. A lot of the teachers are willing to help students in the holidays. Send through an email. If you have a tutor, and I know a lot of students do have a tutor for specialist maths, try and get in contact with them. Really start to show your commitment side of things. But yeah, that's basically all you can do for the holidays to prepare yourself. I wouldn't really recommend getting a head start because you'll only end up confusing yourselves, because this is a subject that needs to be taught. It's really hard to self-learn or rote learn and get it right. So you're better off learning it correctly just once rather than learning it incorrectly and then having to learn it again correctly, which will make a more significant impact on your score at the end of the day. So really, just learning it the first time and learning it correctly is probably the best thing to do. So what I would suggest otherwise is if you have done methods 3-4 or you are doing methods 3-4 this year, try to actually go through that content as opposed to going through specialist maths content in order to prepare for specialist maths 3-4, because I know a lot of students, in my opinion, that didn't do methods 3-4 or hadn't revised methods 3-4 before going into specialist maths 3-4 really did struggle a little bit, just because the methods 3-4 content is actually prerequisite knowledge. So they're not going to teach you, basic calculus like differentiation, anti-differentiation. They expect you to know that, and they're just going to build onto that sort of stuff with the specialist maths component. So really try to, so if you are going to, try to get a head start these holidays, I would actually focus on methods 3-4 if you're doing that, or if you've already done that, just revising the main sort of stuff, so calculus, algebra, all that sort of stuff before going into specialist maths 3-4, as well as spec 1-2 if you have done that. But yeah, that's basically it in terms of the pre-lecture stuff. Now let's actually get into the lecture. So just before we begin, here are some of the topics that you'll be covering this year. We are only going to be covering the first two topics in this lecture. We don't have time to go through everything in a lot of detail, but these are all the topics that you will cover. So vectors and vector calculus, complex numbers, logic and proof, functions and relations, kinematics, differential and integral calculus, differential equations, probability, hypothesis testing, and statistics. So I would say probably the first 4 topics are unit 3, and then the rest are probably unit 4. I personally liked unit 4 much more than unit 3. I just felt like unit 3 was not boring, but a bit challenging. Unit 4 is a little bit more interesting, in my opinion. Okay, so what are vectors? So we're starting off with our first topic straight away, which is vectors. Vectors is a really important topic in Spec 3-4 because you do it with calculus as well, so it makes it even more sort of challenging, and it's sort of more the application side of things. I know I said that methods, specialist maths is not a lot of application, it's just math. There is a little bit of application, and that's mostly in terms of vectors and vector calculus. Because when we learn about vectors and vector calculus, we're sort of getting into the physics side of things. And physics is an application of math. So that is why vectors, when you do them, the questions are going to feel like you're doing application, but they're just going to be testing your mathematical skills. Or the key skills that we're going to go through in this lecture for vectors. So what are vectors to start off with? Well, vectors are basically mathematical quantities that describe change, essentially. Usually change in position, but it could describe a whole lot of things. Change in position, change in, speed, change in velocity, change in, I shouldn't have said speed, I should have said velocity, and I'll tell you why. Change in velocity, change in acceleration, all that sort of stuff. So it's just change which vectors represent. How does something change from point A to point B? It could be point A to point B in time, point A to point B in position. And they have 2 components. So that's the magnitude and also the direction. So magnitude is sort of like how big something is. If something has more magnitude, it's more bigger. That's probably the best way of describing it. And then direction, pretty much the angle that it makes. Using either the north-south system, so either the true bearing system, usually along those lines, but most of the time We're just using angles, basically. Angles to the horizontal, angles to the vertical. Yeah, so basically direction. So what direction is something pointing in? When we look at stuff like distance or speed, we don't know we don't know the direction. We just know the magnitude. So if someone has traveled 2 kilometers, they might have traveled 2 kilometers north. They might have traveled 2 kilometers south. They might have traveled 1 kilometer north and then 1 kilometer south. So returning to the same position. Same for speed. If someone is traveling at 2 kilometers per hour, are they going north at 2 kilometers per hour? Are they going south? Are they going west? So those are scalar quantities. Stuff like distance. Vectors are quantities which have both magnitude and direction. So they provide us a little bit more information. And that's why they're a little bit more useful compared to the conventional sort of stuff. Okay. So next, let's have a look at depicting vectors. So how do we actually show that something is a vector? So you would have seen this in year 11. So I'm not going to go through this part in a lot more detail, but basically a vector, when you're drawing it out, has a tail and a head, and that's basically to show the direction. So for example, in this case, we have the tail on the left and the head on the right. So therefore, the direction that this vector is traveling in, or whatever the vector is representing, is to the right. The length represents the magnitude, and the length is only really important if we are comparing 2 or more vectors. If we're just looking at one vector, like how can we tell what the magnitude? We can literally have the magnitude be anything. But it's only when we're comparing 2 things. So for example, this arrow might be, have a magnitude of 2, but then, sorry, my bad. Just get my pen out. And if I'm looking down, it's just because I'm looking at my iPad. Okay, so if we have a longer arrow, something like this, then that would be a magnitude of 4, where if this magnitude was 2. So that's basically what that is. And vectors we know exist in 3 dimensions. We only have 3 dimensions currently. We don't have a 4th dimension, technically. But so when we look at vectors, we're only looking at vectors in the 3rd dimension. So we'll look at the 3 dimensions in the next slide. But what was I going to say? Yeah. So just something to note is when we are drawing vectors on a plane, the important thing to note here is that it doesn't really matter where they start from or end at. As long as they have the same direction, magnitude, it's the exact same vector. Okay, so that's something really important to note. Obviously, you guys would have covered that in year 11. If you haven't, that's something new to know. So vectors does not matter what direction, does not matter where they're starting from, where they're ending at, as long as the magnitude and direction are the same, they are the same vector. So all 3 vectors here, although they're at different starting positions, they are the exact same vector. Okay, let's get to the next slide. Okay, so this is what I was talking about, vectors in 3 dimensions. Most of the time, I would say 90% of the time, you'll be dealing with vectors in 3 dimensions, which will have both an I, a J, and a K component. I is usually east-west. J is usually north-south. And then K is actually popping out of the page or going into the page. A little bit hard to visualize here, but it's sort of like if I have my flat hand, I component would be going left, right. J would be going up, down, my hand, and then K would be pointing up or going down into my hand or out of my hand. a little bit hard to visualize. You don't really need to visualize it. It's the maths that's important. But sometimes just visualizing it or just drawing a quick diagram really does help. Okay, adding vectors. So this is where we start to get into the math side of things. Basically what we do when we add vectors is we take the two vectors that we want to add. So for example, in the over here, we have u and v. We have u and we have v. So these are the two vectors that we want to add. So basically what we do is we align them so that the head of the first vector touches the tail of the second. So as you can see here, the head of the u is touching the tail of the v. Now because you're just adding, it doesn't matter which order you do them. You could do them as v and then, and then v. You could do it like that. You'll get the exact same answer because like I said, the only thing that matters is the direction and the magnitude. The rest is not important. And basically the actual vector the resulting vector or the sum vector is basically the vector that you get when you draw an arrow from the tail of the first vector to the head of the second. So tail of the first, head of the second. And as you can see, this and this is the exact same vector. So when you're adding them, the order does not matter. You'll get the exact same vector. Here we can see a few more examples. So we have a plus b. This is a bit of a weird one because they have the same, well, not the same, but they have opposite directions, exactly opposite directions. So all we have done is it's sort of like you have subtracted, a part of A. So you've taken off a chunk of A. Sort of thinking it like that. P plus Q, pretty straightforward, just a line from the tail of P to the head of Q. Okay, another thing that's important when it comes to stuff that you're not drawing is actually adding vectors when they're in the I, J, K form. All we do when we're adding vectors in that form is we just add the individual components. So we'll add the I components, we'll add the J components with each other, and we'll add the K components. So as you can see here, 3i plus I gives us 4i. 7j plus 2.5j gives us 9.5j. Negative 2k plus 11k gives us 9k. So that's what happens when we add vectors in the I, J, K form. What about when we're subtracting vectors? So subtracting vectors is so straightforward because it's the exact same as vector addition, just one minor thing. And that is, because we're subtracting something, we need to flip or reverse the direction of the second vector when we're adding. So basically, when we're subtracting. So basically, if we're subtracting these two vectors over here, basically what we need to do is essentially just add them, but what we're actually adding is the opposite of this. So minus this, we flip it, it becomes plus, the opposite vector. So as you can see, the direction has been reversed. And then we just add them like we have on the previous slide. Pretty straightforward. So I'll just do a quick example. So if we have something like, minus this. Basically what we do is we take the same vector. Oh, I think I'm shortening it. Remember, the magnitude is important when we're drawing. And then we add and we flip the direction. So it basically just becomes the vector. And then remember, so we start with the first vector and then we put the tail of the second vector to the head of the first vector. Like this. And then the resultant vector is just going to be the vector that we draw from the tail of the first to the head of the second. So this is our final answer. So I hope that makes sense. Let's move on. Vector properties. So vectors have a lot of unique properties and a lot of things that you'll be asked to calculate when you get a vector. So the first thing that you'll most likely be asked to calculate is the magnitude of the vector. So when we have something in I, J, K form, we have the I component, the J component, and the K component. And that's usually written in this form, the one that we looked at. So before we were just given arrows. The magnitude is pretty straightforward when we're given the arrows. Just measure it using like a ruler. When we're given vectors in this form, however, we need to do something unique, because essentially what this actually is it's telling you how far, so the X next to the I component is telling you how far the vector is left, right from the origin. So if I were to draw a diagram, and I'm not good at drawing these ones. I think that's how you draw it. Anyways, so this is what? X component, this is Y, and then this is Z. So it'll be somewhere, along here, let's just say. So we draw like this, and basically what we're doing is we're calculating the actual length of that vector from the origin. And that is what the magnitude is. And there's a formula. All you need to do is you need to square root. And this sort of is derived from actually Pythagoras. So if you want to look at the full proof, which you might cover in class, I would really encourage you to watch like a video of the proof of the magnitude of the vector. It's really interesting. But otherwise, I'll just go through the formula for today. And the formula is the modulus. The symbol is modulus, and you'll learn that as well this year. But that's how we basically denote the magnitude of something. And the magnitude of R is equal to the square root of the I component squared plus the J component squared plus the K component squared. So we just square root and we square all the numbers in front of the I, J, and K. If we only have two of the components, so sometimes we might just have I and J, then we just, do the same thing, but we just, don't have to consider this. Or if there's no I component, then we ignore that and we just look at these two. So this formula can be altered depending on what you are actually given. Okay, next, another concept that you need to really understand is parallel vectors. So a lot of the time you'll be asked to prove that two vectors are parallel to each other. And basically what you need to understand for that is two vectors are only parallel to each other if, and you'll have to use this particular formula to prove. If U is equal to a scalar multiplied by, the second vector. And basically what that is saying is that if we have vector U, another vector is only parallel if we can multiply the magnitude of U to get V. And that sort of makes sense as well, because V and U are the exact same vectors. The only thing that differs is their magnitude. So U and V, basically the same vector. We just need a scalar K, which is either going to stretch / squish the magnitude. And that's how we prove that something is parallel. If that is not the case, then it's not parallel. So a good example, for this is, let's say we have 2i plus 3j plus 4k. And let's say we were asked to work out whether this is parallel to 4i plus 6j plus 8k. And now what we would have to prove is that, let's say this is u, and let's say this is v. Sorry if the writing is a bit messy. I'm just going to clear this part. Okay. So all we would have to prove is that u that u is equal to k times by v. And we can clearly see that it's some factor of 2, or a scalar of half, actually. So u is actually half of v. Because if we multiply v by half, we'll get 2i plus 3j plus 4k, which is u. So that's why they are parallel. Next, we have the concept of unit vectors. So unit vectors are a special type of vector that have a magnitude of 1. And this is to specify direction. So basically what unit vectors help us to do is they sort of retract the magnitude of a vector to just being 1. And why we sometimes need this is we might just need the direction of a particular vector, but we don't really need its magnitude. So for example, you'll get questions like, determine the vector that is parallel to this, but has a magnitude of, blah, blah, blah. And the way of, sort of doing that is finding the unit vector and then just multiplying the unit vector by whatever magnitude you need. That's the most straightforward way. Other times you might need to use this is sort of sometimes finding angles. Yeah, so a lot of real uses, and also for something that we'll learn a bit later on, which is called a vector and a scalar resolute. You'll also need to find unit vectors for that. But the formula basically is we have the vector. All we need to do to find the unit vector, and the unit vector has this really special hat symbol, is we need to just divide by the magnitude of that vector. So the vector divided by its magnitude gives us the unit vector. Oops. So, next thing, when we multiply vectors together, okay, so now let's have a look at scalar or dot products. So this is when we're multiplying two vectors by each other. Technically, it's not multiplying. It's more so finding the dot product. We really don't call it multiplying. So when we're trying to find the dot product of two vectors, and I'm hoping that you guys have seen this before in units 1 and 2. If you haven't, this is definitely a new concept for vectors, but very, very useful. Dot products are one of the most important things that you'll have to work out, either in proofs or just for like other sort of general calculations. Okay, so finding the dot product of something, how do we actually go about doing that? So to find the dot product of two vectors, all we do is we just add the corresponding components. So for example, my bad. Okay, that's good. Okay, let's just say we have vector A and vector B, and we're trying to find the unit vector for those two vectors. All we need to do is we need to multiply the I components and add it to the product of the B components. I'll do that in a different color. And that is what you can see here. If there's a K component as well, then we do the same thing. Add to the product of the K components. We can only do it for two vectors, however. You can't dot product three vectors. You'll have to do them separately. So you have to do dot product A times dot product. Let's say we had A dot B dot C, which you'll never ever get. This is something you're likely to get, but this in itself you're not going to get because it actually does not. Technically, it does exist, but you'll never, you'll rarely ever get this. But what you'll need to do is find the dot product of A and B, and then do C. So it won't work if you just do A times B times C all together. Another thing to really take note of here is that for the dot products, we will get a scalar answer, which is kind of weird, but that's just how it works. So we actually get an answer that is a scalar, so a whole number. Or if it's a square root, then like a square root or something, but you get the point. We're going to get a scalar. We're not going to get a vector as the answer. Okay, another thing that we need to know is how to find angles. So remember when I said that angles are so important because they help us determine the direction of a vector. Vector angles is a really important concept, and it uses the concept of dot product to actually work it out. So to find the angle between two vectors, we have to use this messy formula, which is basically the cos of the angle between two vectors, and this is used to find the angle between two vectors. Not just the angle of one vector, it won't work, it's the angle between two vectors. And in order to use this formula, there's something that needs to sort of be understood. And that is that the vectors that we're actually trying to find the angle for need to be tail to tail. And I'll show you what that means in a second, but just looking at the formula, it's basically the cos of the angle between two vectors is equal to the dot product of the two vectors divided by the magnitude of the two vectors multiplied by each other. Just a very weird looking formula there, but that's what we need to use to find the angle. And what we mean by the vectors being tail to tail is something like this. As you can see, we have the tail, tail, and then over here, and then we also have the tail here. And this is the angle that we're finding. If it's like this, where you have the head and then the tail, that's not going to work. Some important properties to note of dot products. The dot product of two vectors is just the magnitude of that vector squared. The dot product of two vectors, and if that is equal to 0, then the two vectors are perpendicular. So what that means is it makes a right angle. And that is because we end up getting cos of 90 degrees. And what is cos of 90 degrees? It is just 0. Oops. Okay, so next we have the cross product. So this is the new part of the study design. Students weren't required to know this prior, but basically there's another weird, messy looking formula. And basically the formula's over here. So to find the dot product or the cross product, this is where the symbol actually looks like a cross. Whereas before, when we were finding the dot product, it just looked like a dot. Like this. Now it's actually a cross. So that's why we called it a cross product. So given two vectors A1i plus A2j plus A3k and B1i, B2j plus B3k. The cross product is defined as A cross B. All we need to do is we need to take the matrix of the three components of that vector and multiply it by the matrix of the B components. And that will give us our answer. So here, let's look at a quick example. So find the cross product of 3i plus 2j minus k, 4i minus 6j plus k. So we have our two vectors. All we have done is we have found the cross product. What we have actually done is we've written down the components of the u vector in the first matrix. So the I component, the j component, and the k component. And then we have written down the v components. If there are no components for a particular vector, just write it as 0. So if let's just say for v it was just 4i plus minus 6j, just leave it as 4, negative 6, 0. And then we actually do the cross. You can do this on your calculator, but otherwise there is a strategy to this. So what you need to do is, let me just show. Oh yeah, so this one you'll need to do on your calculator. Otherwise, I would just take this down in my book somewhere. So this formula is really important and it will help you solve the cross product. So A2B3 minus A3B2, A3B1 minus A1B3, A1B2 minus A2B1. So that's what we're actually doing when we are solving this formula. And after we've done that, we will get something like this, a resultant matrix. And that's basically our I, J, and K components of the resultant matrix. And this time we will actually get a vector for the cross product and not just a scalar. Okay, so next we have projection vectors. So if we have a vector like shown above, we will have something called a projection and a rejection. So projection is sort of like the shadow that a vector is making on another vector. So if we had, let's say vector B, over here, and let's say we had vector A going into infinity, we're sort of just seeing, not going into infinity, it stops somewhere. We're sort of just seeing what is the shadow sort of it makes, or where does the shadow stop, essentially. That is what the projection is, and it has a specific formula. And the formula is, it depends on what the question is asking. So if it's asking you, what is the scalar resolute of A, of vector A, in the direction of B, then what you need to do is have vector A dot product it with vector B, and then divide by the magnitude of B. So that is a scalar resolute. It will give you a scalar quantity. And that will be the magnitude of this projection. So the magnitude of this. If we're trying to find the vector resolute, so that will actually give you the vector of the projection. All you need to do is take vector A, dot product it with vector B, divide by the magnitude of B squared, and then multiplied, so doing this will give you a scalar quantity, and that's just sort of like a factor that you need to multiply just the vector B by. So not a dot product, just multiplying it. So a scalar multiplication. And then the rejection, or the perpendicular vector, so that's this vector over here. Well, if we think about it, we know that the projection vector, let me just delete this annotation. We know that this vector over here, the projection vector, plus the rejection vector gives you vector A. So basically, if we already found the projection vector, to find U, or the rejection vector, is just going to be vector A minus the projection vector. And that will give you your rejection or perpendicular vector. So this just gives you the perpendicular distance from the projection or the other vector to A. Okay. So here we have a quick example. Find the vector resolute of A in the direction of B given. Okay, so what was our formula from before? So it was, vector A, sorry, my pen's just being weird. So it's going to be vector A. So we actually don't write vectors like this. They have in the question because I couldn't type out the squiggly arrows. But in an exam or a SAC, this is how you're going to be writing vectors. So vector, oh yeah, that's right. Dot product vector B divided by the magnitude of B squared, and then we have vector B. So basically that is going to be I minus 3k dot product sorry if I'm looking down, I'm just looking at my iPad, minus 4j plus k, divide it by the magnitude of b squared. So what's the magnitude of b squared? That will just be, what's the magnitude of b? Oh yeah, so we'll just work that out in a second. But that's just going to be, remember, root I component squared. Oops. I component squared, which is just 1 squared, plus negative 4 squared, plus another 1 squared. And because it was the magnitude squared, we can just actually remove the square root. It will just cancel out. And then multiply that by vector b. So I'm just going to do that at the end. I'm just going to find what this equals to. So I would encourage you guys to stop the video, or if you're watching it live, just take a moment to do the question. So it will just be, so finding the dot product, all we need to do is multiply the corresponding components. So we have I and I, so 1 times 1, which is 1. Okay, for j, we don't really have a component, so just going to be 0. And then for k, it's going to be negative 3 times 1, which is negative 3. Over the magnitude, so 1 plus 1, which is 2, plus 16, which is 18. And that will just be negative 2 over 18, which is negative 1 over 9. And then we just multiply by vector b. So vector b was I minus 4j plus k. And you can just leave your answer like that. You don't need to simplify it any further. But yeah, that's basically it for the vector resolutes. Okay. Let me know if you have any questions in the chat. Otherwise, we'll move on. Okay, next we have this concept of linear independence. So this is actually really, I wouldn't say complicated. It's a little bit of a challenging concept to visualize or conceptualize because it's in 3 dimensions basically, and something in 3 dimensions is really hard to comprehend if you can't really see it in actually see it. So if you can find like a 3-dimensional sort of thing, usually there's like 3-dimensional visualizers programs. If you can, I would really encourage you guys to visualize this. But basically, what linear dependency is if a vector aligns on a single linear plane. So basically, if we have multiple vectors, and when we put them on a linear plane, so a linear plane is basically X, Y, Z, the graph that I showed you before. If we put on that, if the vectors somehow coincide or they somehow bump into each other, then that's called being linear dependent. They're linearly dependent on each other because they're colliding into each other. So as you can see here, if we put these 3 vectors on a linear plane together, they're going to collide with each other. And that's called being linear dependent. So crossing over, passing through one vector. If they don't do that, that's called being linearly independent. But how do we do that mathematically? So there's a lot of different processes, or not processes, there's a lot of different ways and strategies of actually working this out. But the way that I like to do it is using matrices, because that just really simplifies the process. So the question that you're going to get is going to be something like this. So determine whether the following vectors are linearly independent. Are linearly independent. A equals 3i minus 2j plus k. B equals 6i minus 3j plus 5k. C equals 4i plus 5j minus 2k. And we are trying to see if they are linearly dependent. So the formula that we like to use is if k1 plus k2b plus k3c is equal to 0. So I just like to rewrite that as a vector. So k1, a scalar quantity, times by a. And where do we get that actually? So the way that we get that is basically what we're trying to do is we're trying to multiply this by a scalar, this by a scalar, and this by a scalar. And if we add them up together like this, if it's a triangle, then we're actually just ending up in the same position. Because remember, the way that you find what a vector is, you start from the starting point, which is the tail, and you follow it along until you reach a head, ending up at the same position. That would just be 0, right? So that just means if it equals to 0, then it's linearly dependent. If it doesn't equal to 0, then if it equals 0, then it's linearly dependent. If it doesn't equal 0, then it's linearly independent. Okay, yep. So now looking at this, we are trying to see if k1a plus k2b, so a scalar multiplied by a, plus a scalar times by b, plus a scalar times by c, does that give us 0 or not? So the way that I like to do it is write this in the form of a vector. Sorry, not a vector, in the form of a matrix. So I just wrote down the components. So we have the I components, j components, k components of the 3 vectors, multiplied by k1, k2, k3, and that should be equal to 0. Now we will only find a solution for this matrix. Linear dependency will only occur when there is no unique solutions, when we don't get any solutions for this equation, because that just means that k1, k2, 3 does not exist. So that just means it can't be equal to 0. So that means it's linearly dependent. So basically what we do, instead of actually, trying to do algebra or anything like that, we just find the determinant of this matrix. So I'm not sure how exposed you guys are to matrices. This might be the first time that you're seeing a matrix. And if that's so, just ignore this method. There is another method which your teacher will go through. I'm just teaching this for those that know how matrices work and have used them before. But even if you haven't used matrices, I would really encourage this method. So then what we can do is just find the determinant of this matrix. And what do we know about determinants? If the determinant is equal to 0, so if the determinant is equal to 0, then there is no solutions. If it is not equal to 0, then there is a solution. And in this case, when we find the determinant of this matrix, we get negative 79. So that means there is a solution that exists. So k1, k2, k3 do have values that exist. So therefore, as the determinant is not 0, the set of vectors are linearly independent. But yeah, that's basically it for vectors actually. This was the last topic. Linear independency, definitely a bit of a difficult concept, but definitely something that you'll learn a lot. And once you learn it, there's only going to be mostly multiple choice questions. So you can use your calculator. But yeah, linear dependency, we might go through at the end again, just one more time, or a practice question or something. Okay, so now we move on to complex numbers. But before we do, I'm just going to give you guys 10 minutes to ask me any questions that you have about vectors or anything that I've gone through within this lecture, or just any questions in general. I'm just going to get a quick drink and then I'll be back, and then we'll start on complex numbers. In the meantime, pop through any questions in the chat and I'll answer them. Okay, everyone. Now we'll get started back on complex numbers. Okay. Just a little meme here for everyone. Okay. Okay, so complex numbers. So complex numbers consist of a real and imaginary components. Hopefully everyone's actually had a look at complex numbers in year 11. Definitely I know it's part of the study design, so you would have covered it, but some schools, they don't cover it in a lot of detail, or they just like skim over it, which is probably not the best, because this is one of the most important topics in Special 3-4. But yeah, let's get started. So complex numbers consist of a real and imaginary component and can be expressed in the form z equals a plus bi. And where did we even get the imaginary component from? Well, it's from this. It's from I, which is equal to root -1. So it's numbers that don't really exist, but are made to exist. So that's why it's imaginary. Just some common equations that you need to know. I squared, I cubed, I to the power 4, I to the power 5. I mean, obviously you can do some quick working out and work it out, but just knowing that at the top of your mind is really, really beneficial. And after I4, it just repeats itself. So it's pretty straightforward. If you are given like I36, you know that 4 is a factor of 36. So it's just going to be the same as I to the power 4. Okay, complex conjugate. So the complex conjugate is basically the conjugate of a complex number, and it is denoted by the symbol Z with a line on top, like this. So for example, the conjugate of x plus yi is x minus yi. So whatever the imaginary component is, you just do the opposite sign. So if it's x plus yi, then it's going to be x minus yi. If it's x minus yi, then it's going to be x plus yi. So you get the gist of it. Some properties of the conjugate. So if you multiply a complex number by its conjugate, basically what you get is the magnitude of the complex number squared, and I'll show you how to work out the magnitude a bit later on. Another thing about this sort of stuff is you're not just going to get simple questions like what is the conjugate of this complex number? Like that's too easy. That's probably year 11 stuff. The sort of questions that you're going to get are not even proof questions, more like, and I'll show you some questions a bit later on, but this sort of property is really exploited in multiple choice questions, where I give you a bunch of questions and sort of like ask you which one will give you this, and they give you like some weird answers for the multiple choice. And this z times z conjugate is equal to the conjugate squared is something that not a lot of students really remember or really sort of focus on. So a lot of the questions they forget to answer. And also just knowing off the top of your head that this is equal to this makes solving this so much straightforward. And as much time as you can save on the exam is, going to be so beneficial for you. Okay, so here we just have some basic questions, just sort of like some year 11 revision stuff, I would say. So just simplifying the following. So 2i brackets I plus 3. So just using basic algebra rules. So 2i becomes 2i squared plus 2i times 3, which is 6i. And I squared we know is -1. So it's just going to be 2 times -1, which is 2 plus 6i as our answer. 1 plus I over 2 plus I. So whenever you're asked to solve something like this where it has a complex number in the denominator, this is when you're going to be using the complex conjugate. So what you do is you multiply both the numerator and the denominator by the conjugate of the denominator. So 2 minus I minus I. And that is how you can further simplify this, because then we'll just have a multiplication on the top. And what do we say when we multiply z and its conjugate? We just get the magnitude squared. And the magnitude, we find it the exact same way as the magnitude of a vector. We just square root and square the I and j components. So 2 squared plus 1 squared. Not the I and j. The real and imaginary. What am I saying? So we just square the real and imaginary components, and then we square root it. And then, but remember, it was conjugate magnitude, the magnitude squared. So square root effectively just cancels out. So we're just left with the numerator. For this one, we just use the rainbows method. So 1 times 2, which is 2. 1 minus I, which is minus I. I times 2 is 2I. I times negative I is negative I squared. Negative I squared. What is I squared? I squared is negative 1. So it's negative 1 over 2 squared plus 1 squared. So 4 plus 1 is 5. I'm just going to do my work on the left-hand side. So 2 minus 2 plus 1. So minus 1 becomes plus 1. So we're left with 3 minus I plus 2I, just plus I over 5. And you're welcome to leave your answer like that, or you can expand it to make it 3 over 5 plus 1 over 5I. But yeah, that's basically it for the sort of questions, the basic questions that you're going to get for simplifying. Oh, sorry, I completely forgot there was one more, which is this one over here, using the double rainbows method that we just used. So 2 times 32 is 64. Minus 2I plus 32I minus I squared. I squared is negative 1, so minus negative 1, which is just plus 1. Oh, there's no denominator. Okay. So, adding the real numbers, 64 plus 1, 65. And then the imaginary, so 32i minus 2i, which is plus 30i. So that is our answer there. Okay, here we have some solve the following questions using complex numbers. Okay, so just solve it how you would normally solve a quadratic to start off with. For the first one, just going to move negative 16 to the other side. So we're left with x squared is equal to negative 16. And then we need a square root. So x is equal to positive negative square root negative 16. Okay, so now we encounter a problem. And this is how complex numbers were invented. How are we going to now solve? Because root negative 16 does not exist. So how can it exist? Well, we need to use I. So what is I? So I is negative 1. So we can multiply by negative 16 times negative 1. Oh, sorry, not negative 1. Times... Sorry, what am I doing? Times I. And what is I? Root negative 1. So therefore it will just become positive root 16i, positive negative 4i. Yep, so that is our answer there, positive negative 4i. Okay, next one. Okay, so when you have something like this, I would probably recommend using the quadratic formula. So x is equal to negative b, which is negative 4, plus minus square root b squared minus 4, a is 1, c is 5, over 2a, which is equal to negative 4 plus minus root 16 minus 20, which is negative 4, over 2. So we have negative root 4 in the brackets. That's just going to be negative 4 plus minus root negative 4. Negative 4. Oops. Using I, that will become positive negative 2i over 2. And further simplifying that, it will just be negative 2 plus minus I. So that is our answer there. So those are our two answers for this question. Now, let me know again if you have any questions. I'm just skimming through this because I do want to go through some more exam style questions at the end. Oops. Okay, so here is something that is also very important when it comes to Specialist Maths 3-4. In Specialist Maths 1-2, you might have went over this, but not in a lot of detail. In Specialist Maths 2, we actually use this Argand diagram to actually visualize what we're actually doing in terms of complex numbers. And I'll bring this diagram up many times during the lecture today, as I'm just going through the content. Okay, so how do we actually read the Argand diagrams? It's sort of very similar to the XY linear plane that we're used to. We have an x-axis and a y-axis. But in this case, the x-axis is actually the real axis, and the y-axis is the imaginary axis. So on the real axis, we plot the real values, and then on the imaginary axis, we plot the imaginary values. So here is a few examples already. So for example, negative 1 plus I. Negative 1 is the real component, so it will be over here. And then the imaginary component is I, so plus 1. So that's why we pop it here. Okay, so next, looking at the polar form. So this is something brand new for year 12. You would have... you probably wouldn't have covered this in year 11. So what is the polar form? So the polar form is a way of expressing complex numbers that is different to the Cartesian representation. So the Cartesian representation is what we're used to, so something plus I. So the real and imaginary components. This is polar form. Polar form is a bit different, and the way that it's actually useful is it actually uses the angle and the magnitude of the complex number. So you can sort of think of it as like a vector. Complex numbers are very similar to vectors. Actually, the thinking, I would say, is very similar to the way that you would think of vectors. But there are some minor, subtle differences. Okay, so how does the polar form work? Well, so like I said, the polar form has a r component and a theta component. And the way that it works is we have z equals x plus yi, and we write it in the form r equals cis x. And what is cis? Well, cis of theta is actually just this, cos theta plus I sine theta. It's a shortened version of writing, cos theta plus I sine theta. So rather than writing cos theta plus I sine theta every single time, because that's actually what the polar form is, we just simplify it to cis theta. Just makes it easier for us. So, so this is what it will end up looking like. So r cis theta. Now, what is r? R is the magnitude of the complex number from the origin. And the way that we find that out is using this formula over here. R is equal to the square root of the real component squared plus the imaginary component squared. So very similar to what we have just done before for vectors, as well as what we did for on the last few slides, I think. Yeah. So that's the R component. That is how you find the R component. Now, how do you find the theta component? Theta is the hardest part. And the way that you find theta is actually the angle that the complex number makes with the real plane. And the way that I like to think of it is using triangles. So we have 2 plus 2i here as an example. So we will always have an x component and also y component. So if you've done methods, think of it sort of like circular functions on the unit circle. Sort of think of it like that. We're finding what the angle is. So this is the angle that we're trying to find. So what we basically should do is, there's a very simple formula actually. It's just the imaginary component over the real component. And we find the tan of that. But what this will actually do is it will actually find arg z. We want the argument of z. And I'll show you what the difference is. So arg z is just any angle. And when you do tan image over real, what you're going to find is, sorry, it's not tan, it's tan inverse image over real. That makes sense. You're just going to find the angle in the first quadrant. So when the imaginary and real numbers are both positive. But what about if it's over here? Will it still be 45 degrees? No, it won't, because now the angle that it makes is much greater. So what will we use instead? So then we will need to know what that angle will be in that particular quadrant. So, for example, if it was tan inverse -2 plus 2i, the angle, if we did tan inverse image over real, ignoring the negatives and positives in this complex number, we will still get pi over 4 or 45 degrees. And now it is up to us to determine which quadrant that is in. So what is the equivalent value of pi over 4 in the second quadrant? Well, it's 3 pi over 4, because it's just going to be pi minus pi over 4. And this comes back to the symmetry properties of circular functions. So that's why I remind you guys to have a look at the units 3 and 4 methods and units 1 and 2 methods and spec 1 and 2 content before coming into spec 3, 4, because that is really important in terms of getting, understanding the concepts and being able to effectively apply the maths. If it was here, we would still get 45 degrees, but now we would need to determine whether it's, in the first, second, or third quadrant. And that, if it was in third quadrant, then we have to, set an appropriate angle. However, there is a domain that we need to follow. So this angle over here, it has to be between negative pi and positive pi. Let me just rub this out. So really important, this angle over here has to be in the domain negative pi to positive pi. So it's starting from here, open circle, going all the way around to here. So if we had a complex number in this quadrant over here, instead of having it pi plus, whatever that is, we will have it as negative pi plus that. So really making sure that we always have our arguments in the correct domain. And we'll look at a few examples. Okay, so let's look at a few examples. So first we have convert to polar form. So how do we convert this? First we find the r. So what is the r? Remember, r is just square root 1 squared, so the real component squared plus the imaginary component squared, which is root 2. And then we need to find the theta. So remember, it was tan inverse imaginary over real. Imaginary is 1, real is 1. So what is tan inverse of 1? Pi over 4. That's the base angle. Now, which quadrant is 1 plus I in? It is still in the first quadrant, so that is actually our theta. So therefore, our value is root 2 cis pi and 4. So this is the polar form of 1 plus I. Okay, let's move on. What about 23i? What is that? Now, instead of using this formula, we can just sort of like visualize it. Where is 23i going to be? Well, what's its magnitude then? Its magnitude, without even thinking, is just going to be 23. Because just 23 in the imaginary direction, up. Now, what about the angle though? So, thinking of the Argand diagram, its angle is going to be over here. This angle over here. What is that? 90 degrees. So what is tan inverse of, sorry, let me just quickly think about it. What is tan inverse of, what is 90 degrees? 9 degrees is just pi over 2. So it's just going to be 23 cis pi on 2. And finally, root 3, I'm going to change this one to actually root 3 minus 3i. Okay. First step, finding r, pretty straightforward. Just going to be square root 3 squared, which is 3, plus 3 squared, which is 9. That gives us root 12, which is 2 root 3. Finding tan inverse or theta. So tan inverse of imaginary, ignoring the negative signs when you're doing this, because you just find the base angle, over root 3. Now what is that equal to? And that is just root 3. So what is tan inverse root 3? That is pi over 3. But is pi over 3 our theta? No, it is not, because root 3 minus 3i is actually, thinking about it, in the fourth quadrant. So what is the equivalent of pi over 3 in the fourth quadrant? That's just negative pi over 3. Using our symmetric properties. So therefore our answer is 2 root 3 cis negative pi on 3. So that is how we convert from Cartesian to polar form. Now going the other way around. Going the other way around, polar to Cartesian, all we need to do is write it in the full form that I showed you. So remember, the full form is actually not cis theta, it's actually 4 cos theta. So what is theta? Just sub it in. Plus I sine theta. Simplifying this will give you the Cartesian form. So 4, what is cos 2 pi? That is 1. But what about sine 2 pi? Sine 2 pi is 0. So plus 0i. So therefore our answer is just going to be 4. Okay, so now just looking at the next one, 8 says 25 pi on 3. What we can just do is, before we even do anything, let's just simplify 25 pi on 3. We know that the unit circle repeats itself every 2 pi units. So let's find the equivalent angle in our domain. And our domain was negative pi to positive pi, if you remember from the previous slide. So just returning it to the original domain, we can just subtract 25 pi over 3 by multiples of 2 pi. So how many would we need? What about, oops. So we need something over 3. So 6 pi over 3, 12 pi over 3. Just check. So just subtracting minus 24 pi over 3, which is just subtracting 8 pi, we'll get to the exact same spot, so it doesn't matter. We will just get pi over 3. So basically 25 pi over 3 is the same as pi over 3. So we can just write this as 8 cis pi over 3 as opposed to 8 cis 25 pi over 3. So now, further working on this, we can just simplify it by writing it like this. So 8 cos pi over 3 plus I sine pi over 3, which is equal to 8. What is cos pi over 3? That is root 3 on 2 plus I sine pi on 3. So sine pi on 3 is half, so plus half I. And further simplifying, we'll get 4 root 3 plus 4i. So that is our answer there for this question. Again, let me know if you have any other queries in the chat. Moving on, what is this? Complex operator. Okay, adding and subtracting the complex numbers. Very, very, very similar to, very, very similar to vectors. So if we technically think about this, if we're adding 2 plus I and 1 minus I, and if we shift 1 minus I, to over here, because remember vectors, doesn't matter where they start from, as long as they have the same direction and magnitude, they're the same vector. What do we get? We get 2 plus I plus 1 minus I. That's what we get, that complex number. So just trying to show you the familiarity here. But basically, when we're adding complex numbers, if they are in the Cartesian form, all we need to do is add the real components separately and add the imaginary components separately. But yeah, that's basically it for adding and subtracting complex numbers. Very simple to vectors. Very similar to vectors. Okay, next, multiplication and division. So, multiplication and division. So, some guidelines for multiplication and division is always try to do it in polar form if it's possible. If not, then obviously you'll have to use the Cartesian form, which is a bit messy and gets really ugly really quickly. Polar form is just so beautiful and it's really designed for multiplication and division. And there's 2 really simple formulas for multiplying and dividing. Basically what we do is if we're multiplying z times z2, so z is r1 cis theta r1, and z2 is r2 cis theta r2. All we need to do is multiply them. We multiply the magnitudes, and that becomes a new magnitude of the new complex number. And then we just add the angles. Really being careful when we're adding or subtracting angles is we're taking note of whether the angle is positive or negative to begin with. Similarly, when we're dividing, we need to divide the magnitudes, and that becomes the new magnitude, and subtract now the angles. So for multiply, divide to r, and add, subtract to theta. So that's a rule that I like to follow. Some other really common forms or polar forms of something. So if we're writing the conjugate of a complex number that's already in polar form, we just take the negative of the angle. For reciprocal, we reciprocate the magnitude and we negative the angle or the argument. Okay, here we have a quick question. Simplify, give answer in polar form. So if we want to simplify this, what we need to do is first of all multiply the magnitude. So 13 times 4, that will be 52. Next, what we need to do is we need to add the angles. So 5 pi over 2 plus pi over 6 will give us our new angle. So just adding those will get... And if you're not asked to leave your answer in a particular form, you can just leave it in whatever form is convenient for you. In this case, it will probably just be polar form, because we're doing it in polar form. Five pi over 2, that will be 16 pi on 6. Okay. It looks like we're done, but we're actually not done. What do we know? We know that our domain is negative pi to positive pi. So we need to get our answer to that form. So all we need to do is subtract 2 pi to get it to that domain. So 52 cis 8 pi and 3 minus 2 pi. So cis 2 pi and 3. That is our answer. 52 cis 2 pi and 3. And we just leave it like that. Okay. Next we have the de Moivre's theorem. Again, something new. You probably wouldn't have covered this in year 11. And why do we use de Moivre's theorem? So de Moivre's theorem is really useful when we're putting a complex number to a certain power. So we need the complex number to be in polar form in order to actually use the de Moivre's theorem. So basically what we do is, if we're trying to find what any complex number to the power of n is, all we need to do is we need to take the same power to the magnitude and then multiply that by the angle. So z to the power of n is equal to the magnitude to the power of n, cis, n theta. So n times by the angle. Another use of the de Moivre's theorem is finding roots. So let's just say we are given 4i, let's just say, and we're asked to find the cube root, or, the fourth root. I don't think that has a special root, or the square root, or something like that. Square root's easy. We don't really need to use it for that. But anything beyond a square root, it becomes complicated. We can't really leave our answer as like this. We can't really leave our answer like that. We need to find the actual cube roots, and most of the time they actually exist. Just something to notice here is that when we are finding square roots, we will have 2 solutions. However, when we're finding cube roots, for normal numbers, usually we'll just have 1 solution. But for complex numbers, we'll have 3 solutions. For 4th roots, we'll have 4 solutions. For 5th roots, we'll have 5 solutions, and so on and so forth. And they will actually be equally spaced out on the Argand diagram, as you can see here. So that is a concept that will be applied when we use de Moivre's theorem to solve equations. A little bit of a complicated process, and we will go through a few examples. But basically, when you're trying to solve an equation or find the cube root or something like that, basically what we need to do is first of all write the formula. So let's say we're asked to find, the cube root of something. First step, write the formula. Z to the power of 3 is equal to r to the power of n cis n theta. Convert the complex number into polar form if it isn't already in the complex form. Then we let Rn equal the magnitude and n theta equal the argument, and make sure the argument is in the correct domain. And then this is basically the formula. So z, or the solutions, are equal to r to the power of 1 over n. So if it's we're finding the cube roots, then it's 1 over 3. Fourth roots, 1 over 4, so on and so forth. Cis, theta plus 2k pi over n, where k is 0, 1, 2, 3, 4, depending on how many you need to find. If you're just finding 3 solutions, then k will be 0, 1, 2, and you sub in each one to work out what it is. I'll actually show you an example because that just makes a lot more sense. So let's just say we have this question here. Find the fourth roots of z to the power of 4, 2 plus 2i. First step is to convert it into polar form. So 2 plus 2i, first finding the magnitude, that's just going to be 4 plus 4, just squaring them. That's going to be root 8, which is 2 root 2. Just leave it as 8 to the power of, just leave it as root 8 for now. We'll come back to it a bit later on. Next step, so we're finding z to the power of 4 is equal to, we haven't really found the angle. So the angle, remember, is tan inverse imaginary over real component, which is 1, which is tan inverse of 1. Oops. Which will be equal to pi over 4. So now we have our equation. So root 8 cis pi over 4. Okay, so now that we know our complex number in polar form, let's just write it down. So 8 to the power of half cis pi over 4. Next, we just apply de Moivre's theorem. So remember, we're trying to find what z is. Z is equal to half cis, and this entire thing to the power of 1 over 4. So then, remember how we applied de Moivre's theorem? So the magnitude, we put that to the power. So 8 to the power of half to the power of 1 over 4 cis, and we multiply it by the angle. So 1 over 4 times pi over 4. Just one thing that you need to remember is, remember how I said if we're finding the fourth root, there will be 4 solutions. So how do we account for all those 4 solutions? Well, we just add 2 pi, but that will find us a solution that's not in the domain. We need to account for the fact that it's within the same circle and it's equally spread out. So we actually add 2 pi divided by 4. If it was cube root, then it would be 2 pi over 3. Actually, I have to write k as well, because we don't know what k is, how many times we're adding it. Remember, k was 1, 2, 3, 4, whatever. So that is how we actually find the solutions. Now, all we need to do is simplify it. So it'll just be 8 to the power of 1 over 8 cis pi over 16 plus 2 pi over 4, which is pi over 2. Comma, k is all integers. So k can only be an integer. It's going to be 0, 1, 2. I'm just going to erase this so I can work out the rest over here. So now all we need to do is find the solution. So what does z equal when k is equal to 0? Well, z is equal to 8 to the power of 1 over 8 cis pi over 16. K is just 0, so we can just ignore that next part. What about when k is equal to 1? Well, z is equal to 8 to the power of 1 over 8 cis pi over 16 plus pi 2 and k. Now we need to add pi 2. So it's pretty straightforward now. Once you've found the first solution, you just need to add pi on 2, pi on 2, pi on 2. But remember, that's only when it's fourth root. When it's cube root, then you add 1 over 3, 1 over 3. Oh, sorry, pi over 3, pi over 3. And so on and so forth. So k equals 1. K equals 2 now. z is equal to h to the power 1 over 8 cis pi over 16 plus, and now k is, what is it? 2 now. So it's going to be pi. And finally, k equals 3. Z is equal to h to the power 1 over 8 cis pi over 16 plus, just gonna, k is now 3, so plus 3 pi on 2. And then you simplify it, and then one last thing that you have to do is make sure it's in the correct domain. The angle is in the correct domain. If it's not, subtract or add 2 pi, whatever you need to do to make sure it's in the right argz domain. But yeah, that's basically how you solve complex numbers using, not complex numbers, how you solve complex equations using de Moivre's theorem. Okay, next let's have a look at complex relations. So what are complex relations? So complex relations are relations on the complex plane. Basically, it's sort of like, you know how for just normal numbers we have equations. So like x squared, y equals x, y equals cos x, y equals log x, stuff like that. For complex relations, same thing. We have equations again. But this time, it's called a locus because it's not just an equation. It's thought of as a set of points that satisfy a certain condition. So for example, if the condition is modulus z equals 2, we are looking at all numbers on the complex plane that have a magnitude of 2. And what this sort of pans out to be on the Argand diagram is a circle with a radius of 2 centered at 0. So that's how we sort of look at complex relations. We sort of look at it from a geometric point of view as opposed to an algebraic point of view. Now, what about if we had this? What does that imply? Well, again, it implies a circle with a radius of 2, but now we sort of have like a shift. And that shift is z minus 3. So from the center, we're moving 3 units to the right, plus I, and we're moving 1 unit down. So that is now a circle centered at 3 minus I. Or if you're looking at it in terms of coordinates, 3, negative 1. That is now our complex number. A complex relation. So this is the circle over here. Okay, so we have different types of relations that you will deal with within Special Maths. The first is a circle, probably the easiest one and easiest one to identify. Z minus A, that's the common form. Z minus A equals R. Z is, you just ignore that. Negative A is what our center point is going to be. So if it's Z minus A, then A is going to be our center point. So if it was Z minus, 1 plus, if it was Z minus 1 minus I, which is Z minus 1 plus I, our center point is actually going to be 1 plus I. If it was Z plus 1 minus I, Z plus 1 minus I, what will that be? Well, that will be Z minus negative 1 plus I. So center point is negative 1 plus I. Make sure you return it to this original form if you're trying to work out how to draw it. Because whenever we return to the original form, we can immediately identify that A is going to be our center point. And then R is the radius. Next, we have rays. So rays are basically just straight lines that have a starting point. So if we have argument z minus b equals theta, basically what that is we have, again, a starting point, which is going to be b. That's our starting point. And then we just draw, we just draw a line with that angle that's given. So if the angle was pi over 3, then we draw a line with that angle, pi over 3. And another thing to note for rays is that the starting point is always at the origin and it's always an open dot. Actually, it's not always at the origin. If we have a translation, then it can move. Because if B is like, 1 plus I, then it's going to be centered at 1 plus I. That's the starting point. But the starting point is always an open dot. That's the important part. Okay, and then we have lines. So these are a little bit more complicated. Never do anything related to lines algebraically unless you're told to. The way that we do it is, again, using geometry. So lines are also known as perpendicular bisectors because basically what it is we have two separate points. So we have the point A, and we have the point B. And what we're actually trying to find is the perpendicular bisector to the line that connects them. So this is what we're trying to find. So we're trying to find a line that is equidistant from those 2 points. And we call that equidistant because every point on this line is equally distant from A as it is to B. Okay, so this is how we do them. So we graph the 2 points given, so A and B. We use the midpoint and gradient formula between the points. And that will give us the... so first of all, we find the midpoint between these 2 points. So let's just say we had... Let me use an example. Z minus 1 minus I. And let's say we had Z minus 2 minus I. First of all, return to the original form. Z minus 1 plus I is equal to modulus Z minus 2 plus I. So now 2 plus I and 1 plus I are our original, are our 2 coordinates, so A and B. So plotting it, we will get the coordinates 2, 1 and 1, 1. Now first of all, we find the midpoint between these 2 points. So if you know it from methods, the midpoint is just it's just x1 plus x2 over 2, comma, y1 plus y2 over 2. That is just what the midpoint is. Let me see. Oh yeah, so and then we find the gradient. And the gradient, pretty straightforward, y2 minus y1 over x2 minus x1. Excuse me. That will find you, so the midpoint that we'll find is this midpoint over here. And the gradient that it will find you is this gradient over here. But we're not trying to find that line. We're trying to find this line over here. So what we need to do is we need to divide the gradient by -1. Because remember, gradient of 2 perpendicular lines, so the gradient of a parallel line and a perpendicular line is equal to -1. So to find the perpendicular gradient, we need to divide the gradient from -1. This gradient over here that we found between the points A and B. Once we've determined the gradient of the perpendicular line and the midpoint, we can use this formula over here, y minus y1 over x minus x1, to find the equation. So what is y minus y1? Y1 is the midpoint y coordinate and x1 is the midpoint x coordinate and m is the perpendicular gradient. And then once you find the line in Cartesian form, you can just sketch it. It makes it really easy. Otherwise, if you know how to do it using this, then that's all good as well, but that gets a bit complicated. Okay, so we just have a few quick examples. So first we have Z, okay, remember writing it in that form, Z minus 1 plus 3i. Actually, sorry, it's not that, right? -1 plus 3i. is equal to 4. So what is that? That is a circle that's centered at -1 plus 3i, so centered over here, and has a radius of 4. So that is what that will look like. What about this one? So this is, we haven't really looked at that one, but real we know is x values, and images we know are y values. So x minus y equals 5. That is our equation. And then we just sketch that. And what about argz is greater than pi over 3? Again, this is a little bit more of a complicated one. But what are we actually drawing? Well, we are actually drawing, or what is this relation? This relation is anything that has an angle greater than pi over 3. So it isn't really specified what we're actually drawing here. Usually it's a little bit more specified, but what is pi over 3? Pi over 3 is something like this. So basically it's going to be actually a region, not just a relation. It's actually going to be a region. So it's going to be anything that has an argument greater than pi over 3. So it's going to be actually this region over here. So this region over here, remember it's capital arg, shaded in, has an angle greater than pi over 3. And it actually doesn't stop there. There's no limitations on the magnitude. So actually, this is not a really good example, but it's sort of just to get you sort of thinking about things geometrically. Basically, what this sort of represents is anything that has an angle greater than pi over 3. Oops. Let me see. Okay, so we don't really have any time for any exam questions, but just briefly, what we have covered is vectors. So we've covered additions, dot products, linear dependence, vector resolutes. And for complex numbers, we covered eigendiagrams, polar forms, and de Moivre's theorems, as well as complex relations. But yeah, that's basically it for today's lecture. Thank you everyone for coming to this lecture, and just give yourself a pat on the back for actually picking this subject. It's one of the most challenging subjects in VCE, and the thought of you actually just picking it is like really brave and really courageous just to begin with. I wish you all the best of luck for this year, not just for specialist maths, but for all your subjects in general. I hope you get the scores that you look for. But please remember, VCE is about persistence, dedication, courage, as opposed to just being, generally good at subjects. So good luck everyone for everything. Thank you for coming to this lecture, and if you have any questions, please pop them through now. I'll be monitoring the chat for a few more minutes. Bye everyone.